Hello everyone. So this is a recap of session 6. We missed recording session 6, so I'm doing a revision of that. I'll quickly go through it. Let me share my screen and the video as well. So I hope the screen is visible, the font is okay. So the first problem that we discussed that day was uh, given a number n, we want to print all combinations of numbers from 1 to n that sum up to n. So let's say n is 4. I have candidates 1, 2, and 3, that is numbers less than 4. And I have to take all combinations that sum up to n. Now, permutations are also allowed. So if we look at this example, one of the solutions is 1, 1, 1, 1. So we can repeat a digit, or we can take individuals, for example, 1 and 3, or we can have a mixture of both. For example, we can have 2 and 1, 1. So that is the question. How do we solve this? So solution 1.5. So let us take the, also it's just n. So if underscore underscore name is equal to underscore underscore main, let's see, and so let's say in our case n is 3. What we want to do is we want to define a function print combination, or maybe print combos, and it takes the value of n, which in our case is n. Okay, so we have defined print combos, takes in n equal to n, and it does something. So we will solve this using recursion. So before we go into the code, let's do it on paper. Um, Let me share the entire screen. Yes. So assume that uh, assume that, yeah, this is not. So assume that n is equal to 3 in our case. So our candidates are 1 and 2. So initially we start with an empty set. That is, when I say set, basically we are trying to find the combination sets. So initially we have nothing in our set, and we have two choices. So we either take 1 and we either take 2. We decide to go in ascending order. That is, we first take 1. When we take 1, now we have one element in our combination, which is 1. The sum of this combination is less than n, so we have to go deeper into the tree. So again, we will choose the children in ascending order. So first one will again have an option to take another one. Now the combination becomes 1 and 1. This is still less than 3, so it can go deeper. So we will again take the first child, which is 1, and that is 1, 1, and 1. Now 1 plus 1 plus 1 is equal to 3. So there is no need to check for 2. Think about it. Now, because we have achieved the sum of 2, the next child has to be greater than this one, because we are going in ascending order and there are no repeats within the candidates. So the next one is bound to be greater than 3 if we take the combination, that is 1, 1, and 2. So there is no reason we should go ahead with this. So the moment we realize that we have achieved the sum, we can close this node. That is, okay, you are done. Return from this function. But notice that the parent isn't done yet. It can still check its other candidates. So it will go to 2, and now the set will be this one plus 2. So 1 and 2. This also becomes 3. Now, because we have achieved 3, there is no reason to go further down. Okay, so we will close this function as well, and we will return. Both its children are done, so this is also done. And now it will go back and go to the other side of the tree, and we will repeat the same thing there. So let us delete, or maybe let's just go ahead with it. So 2 will also have 2 children. It will first take 1, which is because we're going in ascending order. So we will have 2 and 1, and this also sums to 3. And because it sums to 3, there is no need to check the other child. So our solutions will be 2, 1, 1, 2, and 1, 1, 1. Notice that these are essentially the same, but because repetition is allowed, as we said, no, permutations are allowed. So 1, 2, and 2, 1 are both viable solutions. So our solution is 1, 1, 1, 1, 2, and 2, 1. So how do we do it in code? So this is obviously a recursive function. Now let us go over to the code. So what we want to do is we first need some candidates. So let us generate candidates. So candidates is equal to range n. And this is 0, 1, 2 up to n minus 1. So we have the candidates. So because we have to go in ascending order, we will do for C in candidates. That is the candidate. What do? We create a new combination. That is our yeah, let's say new combo. Our new combo is equal to uh, this thing C, okay, and then we check if sum of new combo is equal to n. There is no need to go further, and we will print new combo and return. Returning basically means terminate the function. When you return, the entire function collapses. So we won't check rest of the candidates, and won't go deeper into the tree. So this is exactly as we did in this case, right? So this is one thing. Now, what if the sum is not equal to n? What should we do in that case? Else, we call print combos again, which is the same thing as going deeper into the tree. That is, here the sum was not equal to 3, so we went deeper. Going deeper into the tree basically means calling the function again. So we call print combos again. Now n remains the same, n is equal to n, but we want notice that here whenever we went down, we supplied this item with it, and the next time we went further down, we supplied 1, 1 again here, 1, 1, and we basically appended the new item to it. So we should add another argument, that is a combo. What is my current combo? So when we call it at the beginning, notice that we had 5. 5 is essentially an empty set. So let us say combo, and combo by default we will set it to this. Okay. So we have combo, and new combo becomes basically combo, old combo concatenated with a new one. Okay. So initially this was empty. So now this would be equal to this. So we have new combo, and sum of new combo is equal to n, and we print it otherwise this, and we call it again with combo, new combo, and I think this much should be enough. So let us try Python CD solutions, Python solution 1. Acceleration, I think we missed something. For C in candidates, we have new combo is old combo plus 1 if the sum of new combo is equal to n. We will print the combo and we will return. Else, we will call print combos again. N remains the same. Does n remain the same? Yeah, n remains the same, and the combo is equal to new combo. So why should this fail? Does it print anything? It does not print anything. Combo. Okay, so let's debug this. We have run debug Python. We have candidate, new combo becomes 0. If sum is not, we call this again. For scene candidates, new combo becomes 0, 0. Oh, wait. We should not have 0. Yeah, we have to start at 1 because otherwise it will go indefinitely. Does this work? Yes, this works. So we see 1, 1, 1, 1, 2, and 2, 1, which is exactly the same. So 1, 1, 1, 1, 1, 1, 1, 2, and 2, 1. This is Flutter, so let's remove the annotations. Yeah. So there is one inefficiency in this code. Let us say n was a very big number. Let's say it was close to a million. Okay. It was a million. So what are we doing here? When we have n, we have a candidate and we are generating combination. So let's say I have a very huge combination at some point and I need to call this recursive function. When I call the recursive function, I check summation is equal to n. Every time I call the function, I recompute the entire sum, even though notice that whenever we go down a tree, we reuse the previous combination and just add one number. So why don't we compute the sum at every step and just add one element to that summation? That is, let's say we come here, we compute new combo. Why don't we do new sum as well? That is new sum is equal to sum plus c. And we will take initial sum as 0 because we don't have anything there. So initial sum is 0. By the way, sum doing it like this doesn't work because this is a function. That is why we use an alternate question, that's an underscore. So we have sum plus c and we have new sum. And now what we can do is instead of summing every time, we can just say if new sum is equal to n, we do this. And the next time we call it, we say sum is equal to new sum. So let's see if this works. Solution 1, again depth. So what did we miss this time? The initial sum is 0, which is correct. So for C in candidates, new combo is combo plus C, which is okay. New sum is sum plus the candidate, okay. If the new sum is n, we print, we return. Otherwise, we supply sum as new sum. So what's wrong this time? So we have run start debugging. Machine candidates. Oh, I've supplied a very big number. That's the case. Yeah, because we supplied a very big number, we have to explicitly set that recursion depth because by default it's a smaller value. So it still works, and this is more efficient than the previous case. Now let's move to the second question. The second question says that you have to repeat the first problem, that is again find the combinations, but this time permutations are not allowed. That is, let's say we have this case, that is we have any repeats here. 1 1 1 2. Yeah, for example, this one 1 1 2 and 1 2 1. These are two permutations of the same thing, that is 1 1 2. So what we want to do is we want to remove repeats and we only want to keep unique elements. So in this case, there are only unique elements. 1 2 1 is not there, only 1 1 2 is there. So how do we do this? Now, obviously, we will use this structure again. The only thing is that we have to identify duplicates. So one way to do it is okay. So the first question is how do you compare basically two sets? For example, in this case, if I gave you 1 1 2 and 1 2 1, how will you say that they are the same? So the way to do it is you will first sort them. Let's say you will have 1 1 2 is already sorted. 1 2 1, once you sort it, it also becomes 1 1 2. Now you can compare the two and say that okay, these two are actually identical. So one thing is that we will sort it. Now think about it. We will go through all of the combination, that is whenever we hit a new combinations, we will check that sort, we will sort the new combination and we will compare it with every combination that we have seen before. That is the naive solution. Okay. So for that, we will have to maintain a list of all the combinations that we have seen before. Okay. In our solution one, we were not maintaining anything. We were, if we find something, we just print it out. And for example, if we wanted to store it, we could just write it to a file. So this is efficient in that case that we are not consuming any RAM. But let's say I give you again a very large number, let's say like this. Now think how many combinations you will have. Even if I supply n equal to 15, I think the number of combinations is still close to, I think in the thousands. It already goes to the thousands, even if you are in double digits. So think about if you have a very big number. So this number will quickly explode the number of combinations. And if you try to maintain all of that in your RAM, so you will definitely hit a memory error. So there has to be a better solution to verify that whenever I see a new combination, I haven't seen it before, or I have seen it. I have seen it before. So there is actually a neat solution to that. So let's erase this. Okay, let us do this again. We had five. Wait, we have five. We get 1, 2, and then we went to 1, we went to 1, and in this case we went to 2, here we went to 1, and that is it. Now we are doing it in ascending order. Now imagine that 1 and 2 are instead A and B. Okay, they are instead A and B. So we have 5, we have A, we have B, we again have A, we have B, we have A, and in this case we had A. Whenever the trick here is that we have, let's say we had A, everything on the left of A is lexicographically smaller than A, okay? And everything to the right of A is lexicographically greater than A. Now, what does lexicographic mean? It basically means, for example, you sort something in a dictionary. In a dictionary, if you see the words are ordered in alphabetical order. So AA is smaller than AB, basically. So you compare the first one, A and A are the same. You go to the second letter, A and B. A is smaller than B in the alphabetical order. Therefore, the string AA is less than AB. Now, because of the way we iterate through the tree, we always go to the smaller ones first. We will go here, then we will go here, then we will go up the tree, then we will go down the other side. Okay, we first complete the left hand side, then we will go to the right subtree. Okay, then we go further back up, we go to the right tree, again we go to the left hand side. So notice that at any time, I have seen everything left of me. Okay, let's say I am here. I have already seen everything left of me. So in case I want to check, that the combination that I have here, for example, at this point, my combination will be uh, BA at this point. So have I seen BA before? So what I will do is first, obviously, I have to sort BA. It will become AB, right? It will become AB. I have to check whether I have seen AB at any point before or not. Now, the way we do it is when we traverse the tree, we will keep track of the biggest combination that we have seen. Biggest in this, that is AA is smaller than AB. So what is the biggest string that we have seen? So let's traverse the tree. Let's say we had A, then we had AA, then we have triple A, then we had AB, then we went back up to B. So B is at currently the biggest one, so B, and then we went to AB. Okay, so this is the biggest thing that I have seen at the moment. So the thing is, if the new combination is smaller than the biggest combination that I have seen yet, that is AB is smaller than the biggest one I have seen yet, it means that this must have occurred before. As I said, as we said that um at any time, let's say I am in this position, anything smaller than that, I have seen it before. I must have seen it before because we traverse in smaller to greater order, in ascending order. So if my biggest string is B and the current combination is smaller than that, it must be that I have seen it before that. Okay. I have seen something greater than my current combination, that is B. If I have seen that, it means everything smaller than that, I have already seen that. And since I am also smaller than the greatest element, I must have occurred in the left hand side before as a duplicate. So therefore, we should not consider AB again. Okay. So this is a very neat trick. So let me revise. Let me recap. So because of the way we traverse the tree, every time we go left, it is a smaller element. Every time we go right, it is a bigger element. At any point in the tree, everything left of me is smaller than me. Okay. If we keep track of the greatest element that we have seen, all we do, let us say the greatest element is G, we maintain it in G. Every time I hit a new element, I compare myself with G. If I am greater than G, it means I am the new max. And you cannot, I mean, there is no way you have seen me before that because everything left of me is smaller than me. If I am smaller than the greatest element, it means I must have occurred on the left hand side of G. Okay. And if I have occurred in the left hand side of G, that means I am a duplicate, right? So this is obviously an efficient solution because at any point in time we are maintaining only one combination in the RAM, that is capital G, the greatest combination as compared to all of the combinations. So let's put this into code. So we have, yeah, let's use part of solution one. So we have solution 2.py, and we have print combos. So in this case, what will change? So first we have print combos, again same as before. We have combination, we have sum. Now this time we have to maintain a max combination, and notice that the max combination should be a global thing because every function uses the same max combo. Notice that in this tree, oh, we close that. In that tree, every child, every node, every leaf was accessing the same global maximum. Okay, so we will define the max combo outside the function, and by default we will keep it an empty string because we haven't seen anything yet, and an empty string is smaller than every other string. So we have max combo, and because we have to use a global value inside the function, we will say global max combo. We basically tell the function that is use the global max combo, don't define your own max combo. So we have done that. Now for scene candidates, we do new combo, we do this. Now, if new sum is n, we before we print it, we obviously have to check duplicate, check whether duplicate. So how do we do that? So first we have to compare it with max combo. Okay. So for that, we need a function that can compare two combinations. So how do we do that? So let us write a function to compare two combinations. So define, let's say first combo is greater. That is, if I supply two combinations C1 and C2, it will return true if the first combo is greater than the second combo. So how do we do that? So we need another function that can convert combo to string, right? Because we have to compare strings, we have lists. So we have convert combo to string, and we have to supply C1. This will give me C1. Similarly, C2, or maybe S and S1. So we have again, we will use convert combo to string and C2. So how do we convert a list? Let's say something like 112 into 112. Okay. And is this even a correct thing to do? Let's say 112 conversion to 112. Let's say I had 110 and 2. So this would become 1102. Now, how do you know this is 10 or this is 11? I mean, is it a double digit number or so? So it is better to do it using dashes or some other delimiter. So we will have 1, 10, and 2. So this is our goal. Convert a list into a string where we space them out using some character. So the way to do it, let's say we will create, because this is a one line function, we can do it using a lambda function. So let's say convert combo string is equal to lambda, and what we take, we will, let's say, take x. No, let's say we take a combo, and what do we do with that? We return dot join character for, no, just I for I in combo, and we have to convert this to string. Yeah, so we convert every element of the combination into a string, and we join it using dash. So we have convert combo to string. So we have two strings. Now, if S1 is greater than S2, return true, else return false. And we can write this in one line, that is return true if S1 greater than S2, else false. Okay. So we have comparing two combinations. So compare with max combo. So if first combo is greater, so what do we want to be greater? We want a new combo to be greater. So we'll supply this, and C2 will be our max combo. If that is the case, the max combo now becomes new combo, and we will print the combination. Okay, we print the combination, and yeah. Now notice, even if this was a duplicate, we have still hit n. The sum has still hit n, so there is no need to check further candidates. So outside the if, we will return. Okay, there's a mistake that we did in our session, that is we put return inside the if condition. So this will only terminate if you see a duplicate. But notice that whether you, irrespective of seeing a duplicate or not, you have reached the sum. So you should return either way, whether the if condition executes or not. So you do return. So is everything done? Let us say for scene candidates, we have a, oh, we did not sort that. Yeah, we have made a mistake. Yeah. So the mistake is new combo. We should sort it in place. So we have sort the combo. We get new combo, we get new sum. If the new sum is n, we will sort it. If first combo is greater, that is C1 is greater than the max combo now becomes new combo, and we will print it and we will return. Otherwise, we call it again. So let us try this. So we have Python solution 2, 1, 1, and 1. Yeah. So wait, 1, 1, and 1. We get n equal to 3. N equal to 3. We're making a mistake. Rule max for scene candidates. We have a new combo. We have a new sum. If new sum is equal to n, we sort new combo. And if the first combo is greater, that is, if S1 is greater than S2, we return true. That is, it is a new combo. So we will say max combo is equal to new combo. And in fact, let us write it as this because the combinations are less. So max combo becomes new combo. We print the combo and we return. Else we do this new combo and new sum. Right. Should we sort irrespective of that? No. There's a foreseen candidates. What are my candidates? Range 1 to 3. Okay. So for scene candidates, we have new combo. New combo is 1. New sum is 1. If new sum is equal to n, which is not the case, we go to else and we supply new combo. Okay. Then again, for scene candidates, new combo, we have 1 and 1. If any sum is equal to n, wait, sum, new combo. No, everything, yeah. So new sum is not equal to that. We call it again. For scene candidates, new combo is 1, 1, 1. So this should be in that. So the new sum is equal to 3. If new sum is there, we say new combo dot sort. So it remains 1, 1, 1. If first combo and max combo, so let's go here. So we have S1 and S2. So what is S1 and what is S2? So S1 is 1, 1, and 1, and S2 is this one. So we want S1 to be greater. So is S1 greater? S1 is greater than S2, which is true. So it will return true. So we have max combo is equal to new combo, or we are printing combo. We should print new combo. Let us try it without it. Debugging, yeah, solutions, Python, solution 2, and we have 1, 1, 1, and 1, 2. And notice that if we had solution 1, we had a repetition 1, 2, and 2, 1. This time we don't have a repetition. So I think that is enough. Yeah, Piyush, so this wasn't a regular session. I was just doing a recap. So you can join in the. I'll just post this one on YouTube for the other students.